Good morning. Today we will see two concepts which are related. We have so far seen how to generate an FIR filter. Of course, we have seen the IIR case also, but that is the Wiener filter problem. But we have solved for the filter coefficients in case of the FIR filter using the what is known as the normal equation. So today we will see two analogous development. Firstly, we will see how to solve for a very close problem which is called the least square problem. Previously we used to call the problem a minimum mean square error problem, MMSE. Now we are talking about the least square error problem, or the LSE. So that is the first thing, and the second thing is that we will also look at the IIR filter design problem, not only the FIR problem. So first of all, let us see what is the LSE problem. So in the LSE problem, what do we do? The LSE problem says that given a set of measurements, it is just like the MMSE problem. Only thing is that it says that given a set of measurements yn and xkn, we want to find a set of coefficients ck such that if we compute and estimate y hat n, this is not yn, this is y hat n, using m values of xkn, and then weighting them linearly with ck. So this is an FIR filtering of xkn. If we compute a y hat n, then what are those coefficients ck such that if you define an error as yn minus y hat n, then this sum of these errors over the n, here n varies between 0 to, let us say, actually we should say 0 to n minus 1. N varies between 0 to n minus 1. So find those ck's such that this sum becomes minimum. So what is the difference with the minimum mean square error problem? It's very similar. There also we wrote exactly this equation and formed this error. Only thing is that there, rather than writing this, we wrote expectation of E square n, if you recall. In the minimum, it is a minimum mean square estimation problem. So rather than writing the sum of errors for these data points, there we wrote expectation of E square n. That's what we wrote in the minimum mean square error problem. Actually, they are absolutely similar. So now let us compare the minimum mean square error problem with the least square error problem. Firstly, we note that whenever we write expectation of E square n, so we are talking about not only we are talking about this particular data, we are given some data points, but whenever we are computing expectation, we are computing expectation over the whole, over all possible realizations of yn and xn, because we are actually weighting it using the probability density function. So we are thinking of many experiments. This particular yn and this particular xn that I am getting is just one outcome of the underlying experiment. See, yn and xn are random processes. So every time I perform an experiment, I'll get one set of signals yn and another set of signals xkn. So that's just one realization of the stochastic process. Next time I do an experiment, I'll get another set of yn, another set of xk. So when I am constructing and when I am posing the MMSE problem, it says that the E square n, if we take an expectation over all possible realizations of the stochastic process, then that will be minimum. So we are essentially talking of all possible realizations of the stochastic process. That is, today you do an experiment, you get one yn signal, you get another one set of xkn signals. So if you use those ck's, you will get some ek signal also. Tomorrow you come and do another set of experiments, you get another yn signal, another xkn signals, you again use the same ck and you get another en. Like this, if you do many experiments, then all those ens if you collect and if you take an average over them, then it will be minimum. So it essentially talking of many experiments which you are performing, does not talk of any particular set of data. While in the least square problem, look at this, that our performance index is defined in terms of this particular set of data. We are not talking of any expectation. We are saying that we are given this yn and we are given these xkns. Now find out a ck such that over this data set this error is minimum. What will happen for the other data sets, we don't know, and we are not talking about them either. We'll be happy if this particular data set error, sum of error is minimized. This is the essential difference between a minimum mean square error estimation and the least square error estimation. So one is talking of ensemble averaging. It is computing the errors over many experiments when it is computing the mean, while the other is doing a time averaging. So the other is saying that some en over time, right? This is actually a practical version of the MMS. So since now once we understand this basic concept, we can realize these points. For example, obviously if we are talking about the whole stochastic process, that is all realizations, and if we want to obtain a solution which will be optimal over all possible realizations without talking of a particular data set, then naturally I have to know the property of the stochastic process itself. How can I minimize an error over all possible realizations of a stochastic process without knowing its properties? It's not possible. So therefore we have found that we need to know what was our solution. Our solution for the optimal problem was RC equal to D. The solution of this equation. So what is R? R is the second order moment of X. Similarly, what is D? D is the cross correlation. R is the autocorrelation function of X. D is the cross correlation function between X and Y. So we need to know these things. So we need to know the cross correlation and autocorrelation functions of the underlying stochastic processes. Without this we cannot find an MMSE, right? On the other hand, the LSE does not need any such thing. So even if you don't know the properties of the underlying stochastic process, you can always compute an LSE given a set of data. So it's a much more, it can be always found out. Does not require much knowledge, much prior knowledge. Everything is calculated based on data. So it's a very practical, technique which can be applied in all situations. That is why it is so popular. So this is the first thing, that the MMSE needs second order statistical properties excuse me, of the data, while LSE does not need to know any second order properties, it just uses the data itself. Second thing is what I said just now, that the MMSE is optimal for all realizations of the process. LSE is optimal only for the given data set. It doesn't say anything about what will happen if you use the same set, if you use the same weighting coefficients. Suppose by given one data set, you have computed some optimal weights in the LSE sense based on that data set, and you have got some CKs. Now, if you use those CKs for another data set, what will happen we don't know. We may get a very poor error, lot of error we may get. LSE does not talk about that at all. Okay. So the LSE is optimal only for the given data set. The MMSE uses ensemble averages and the LSE uses time averages. So naturally now you know that if the process is ergodic, then the LSE, if you take long time average, then the LSE will approach the MMSE, right? Because ensemble averages will be equal to long time averages. Similarly, if the similarly you may ask that, okay, MMSE will use a second order statistical properties. Now, how am I going to get second order statistical properties? Right? So one way of obtaining second order statistical properties is to actually do ensemble averaging. That is, actually perform many experiments. For each experiment, compute autocorrelation function, and then sum them over the ensemble. Then you will get the second order properties. But remember that what we said is that if you are given one sequence, how can you estimate the autocorrelation function? So we wrote that it is Rxx. Can you see this on the screen? So you saw Rxxl is equal to 1 by n sigma. This is xk minus l, and if you have this will go from say k will go from l to n minus 1. So if you are given a finite sequence of data, this is how if you are given one finite set of data from where xk values are available from 0 to capital N minus 1 n length sequence if you are available, then this gives an estimate of the autocorrelation function. We had seen that. So if you are suppose you are given one set of data. Now if you say that I want to use the MMSE, how will you get Rxxl? How will you get this matrix? So you say that, okay, I will now approximately compute Rxx using this formula. Then, though you are saying that you are using second order properties, actually you are computing using time average. So therefore your solution will tend to the LSE. So they are actually very related. I mean, that's why I thought that rather than coming back to them at a later time, this is the time to discuss them, because you get absolutely similar equations, everything similar. Okay. So therefore we have a very similar problem. Only thing is that what we are trying to say is that we are in the least square problem, which is a more practical version, does not require much prior information. You can apply always to a given set of data. You can define a least square problem and then solve it, even when you don't know much about the underlying stochastic processes, right?
Can MMSE be seen as a sum of LSEs? If we break up MMSE?
Yes, in the sense that if you can later see that, suppose you have taken an LSE problem, and then if you you get an LSE estimate. Now if you try to take an expectation over this LSE, that is, if you say that I take 1n minus 1 sequence, I define an LSE problem and I solve it. Next time I take another sequence, on that sequence I define another LSE problem and I solve it. So I get another different set of CKs now, because an LSE problem solution is always particular to that sequence. So in this way, if I do it over many realizations, every time if I define an LSE problem and if I solve it, then I'll get a different CK. So now my CK itself, I mean the set of CKs are itself random variables. Now if I take an expectation over the expectation of these random variables, what will happen? So we will see what will happen, and we want to know, I mean we want to know whether this expectation has certain good properties, because typically what will happen is that why do we construct an estimator? You see, while we are constructing the estimator, there are two phases. In one phase we will design the estimator, and in the other phase, practically speaking, we will use it. So if we have a stochastic process, then while we are designing the estimator, we will use certain data points. So we will essentially design based on certain set of experiments, and then we'll design, and then we'll arrive at some numbers, CKs. Now naturally we are going to use these CKs on other realizations, because once we have designed, we are going to use it. So then we will use it on new set of data, and that will give rise to new sets of errors. So now the question is, we are always interested in this question, is that suppose we had designed based on those data points on which we are using. We had optimally designed some CKs with respect to those data points, and now I am using a CK which I have used based on some other data points, and I am using it on them. So what is the difference between these two CKs? Right? So in other words, we would like to know several properties of the estimator. That is, if we take an expectation over all things, does it converge to the MMSE? We will answer these questions, right? So we will derive the LSE absolutely similar. That's why I have not written all the equations. That you can, I have directly written this. You see, if you want to understand how this equation is written, you can understand that En is equal to Yn minus sigma, let us say k is equal to 1 to n x ck xkn. Okay, this is my En at any time instant n, right? So if I now stack these e's, if I now stack this E1, E0, E1, E2, E3, stack them in the form of vector, I'll get this vector. All these y's will also get stacked, so I'll get this one. And this sum is equal to what? Is equal to, you can write x transpose C. You can write this x is a vector, this x transpose is x1n to xkn transpose, and it's a column vector. Now x is a column vector, so x transpose is a row vector, so x transpose is nothing but this vector, and C is a column vector, C1 to Ck. Can you read this? I don't know, this is probably too small. Yeah, I'm just trying to organize now. So the first equation becomes En is equal to Yn minus x transpose n Ck. Rather C, not Ck. Next equation will become Em is equal to, just writing Ym minus x transpose mc. So I can stack them, all these X transposes, then I will get the matrix X. Correct? So I have written this vector matrix equation directly. This looks absolutely like that previous thing. There also we wrote the same equation because we were using the same error equation. So again we can write a sort of performance index in terms of this incidentally now this X is a matrix, C is a vector. This should not be over bar, it should be under bar. So now we can again write what is now my performance equation. It is nothing but E transpose E. Sum of, you have to know these matrix manipulations. One vector, row vector into column vector means sum of squares. So if you just multiply y minus xc transpose y minus xc, you will get this. This is very simple. So now you differentiate it with respect to C. Every time I have written over bar, actually there should be under bar. I am saying under bar just to indicate that this is a vector, because I cannot write bold or anything. So now if you differentiate it with respect to this expression, if you differentiate with respect to this vector, again every time I am repeating that this is a scalar, it's a number, this is a vector. So it means that it is basically dpc by dc1, dpc by dpc by dc2 and so on. This vector is denoted as this. Okay. So this is, if you just do it term by term, you can always do it term by term. Write a matrix as x1, x2, x3, x4. If you don't understand how it is happening, first time you can always write it in terms of scalars, actually write this expression in terms of the matrix elements, and then really differentiate with respect to C1, with respect to C2. You can do that, and then you will find that if you differentiate this and then set to 0, you will get this equation. This is nothing but the same normal equation. Only thing is that previously this is R now. There you got R because you had an expectation. Now you don't have any expectation. You are only doing it with respect to that data set. And this is like D, cross quantity between y and x, right? So you get the same normal equation, and now so this is, what is the dimension of this matrix? What is the dimension? I have written x transpose x inverse. Is it invertible? Is it square? N by n, capital N by capital N, n for north. It's capital M by capital M, where M is the number of terms here. Sorry, this should be M. This one. That is the order of your FIR filter. N is the number of points. M is the order of the FIR filter. In the estimate, how many terms you are taking. See, when you are doing an FIR, why I say FIR, because this is a very general description. You can always write that xkn is equal to xn minus k. You can always define xkn in that way. Then it will become a true FIR filtering. Now it's not, I'm saying FIR filter, but it's not. It's actually as if data is coming from capital M different sensors, and we are making them sum. This equation looks like that. So it's an M into M matrix. It is square, but we don't know whether it's invertible. So how are we writing this? So we can only write this provided it is invertible. So when is an M into M matrix invertible? When its rows or columns are linearly independent. Then only it is invertible. Now, first of all, why it should be linearly independent? First of all, remember that this is a composite matrix, which is, remember that if you multiply a matrix A by a matrix B, then the rank of AB can never exceed the rank of A or B. So this has to be of rank M. This only then X transpose X inverse can have full rank. Otherwise, this M into M matrix will be singular, and you cannot solve this problem like this. So when will the matrix X will have a rank M? Matrix X has how many columns, how many rows? Matrix X has capital N rows, because we are writing, stacking it in terms of data, and it has capital M columns. So first of all, for any non-square matrix, the maximum rank is the minimum of number of rows and number of columns. Rank can never go beyond that. If you have a 3 by 2 matrix, maximum rank can be 2. So the rank is going to be minimum of n and m. So firstly, if n is less than m, then you cannot solve this problem, because then the rank is going to be less than m. And so if you have number of data points which are lower than the number of the IIR filter, then obviously there is a solution. I mean, right? But it is not guaranteed that if you use the just if you use more number of data points than m, this matrix is going to be invertible. If n is less than m, no question of being invertible. Even if n is greater than m, now it may or may not be invertible. So you should choose such data points such that it is invertible. Otherwise, there is no solution, right? So we have to remember that this thing is incidentally called a pseudo inverse, because if in this equation x was invertible, x itself was square, suppose it was, then you would have calculated C as x inverse y, but it is not square. So if it is, it is actually rectangular. Still, you are in some sense you are trying to invert this term. So that is why it is called a pseudo inverse, or sometimes it is called a Moore-Penrose inverse, named after the scientists who have discovered this. So actually, what you are doing, what are you doing? You see, when n is greater than m, how many unknowns here? Capital M number of unknowns, because so many so many coefficients of the filter you have to solve for. And how many equations? Capital N number of equations. So if you have 5 equations and if you have 3 unknowns, what solution do you get? Linear equation solving. No. Either you don't get any solution, you in general don't get any exact solution. If you have 5 equations and you have 3 unknowns, if you have 3 equations and 3 unknowns, and if the equations are independent, you always get a unique solution. If you have more equations than unknowns, then in general you cannot solve it. That is, there will be no value of those unknowns which will simultaneously satisfy all the equations. That is the general situation. But in some cases of those equations, it might. If you have 2 equations and 3 unknowns, then you have an infinite number of values of the unknowns which will satisfy those 2 equations. Okay, so so this is about the solution of this equation, and this matrix invertibility is a key issue in being able to compute the estimate. Okay, so now we are coming to your question, that what are the statistical properties of the LSE? It is important because we are going to design it based on some data sets and we are going to use it on other data sets, right? This is called a generalization property. Okay, very important, for example, very important for neural network training and other things. Whenever you construct an estimator like a neural net, is an estimator. It's a nonlinear estimator which is very popular. You have to ensure, you have to train it to ensure that you have a generalization property. That is, it will not only fit this data set well, but it will fit other data sets well as well. There is a key property. Okay, sometimes it may happen, especially with things like neural networks, it will happen that they are so powerful in the sense that they can match almost any data set. I mean, once it happened that I'm just giving you this example, that I was trying to model the load variation in the city of Calcutta using a neural net. So the load variation in the city of Calcutta, electric power load variation, if you plot, you will have, it's typically a periodic series. First of all, there will be a period over an year. During summer, load will be more, during winter, load will be less. This will repeat summer, winter, summer, winter. If you go little inside, you will find that there is a smaller period over weeks, right? Typically, depending on the industrial activities, nature of the load, you will find that maybe every Monday's load will be slightly higher than every Wednesday's. So in the week there is a cycle which repeats over weeks. If you go in a day, you will find still smaller cycles, right? In the morning it will be low, around 9-10 you will get what is known as the morning peak. It will come down, again you will get an evening peak. So it also cycles over a day. So you get, generally it's random, but you get a periodic pattern. So I was trying to model it. Now what happened is that load is going, suppose one particular day I was plotting for a year, there was some political meeting or something happened, so that the load just fell and then it rose again. So that particular data set that I was using had this kink because of something peculiar there. Probably there was some accident happened, or maybe some band or something. So the electric load fell. Now when I was using a neural network, my neural net, actually this is a peculiar problem with neural nets, does not generally happen with other kinds of estimators, but I am mentioning it just to emphasize the point on generalization. My neural net, if I train it, what I am trying to do, I am tweaking the weights of the neural net such that this data set is nicely approximated. So I am actually solving an LSE problem, but my model is not this. My model is a much more complicated nonlinear model. So my neural net actually modeled this. It was so powerful that it modeled this kink also. Now the point is, if it models this kink, then on this data set the estimator has performed very nicely. But its generalization capability is seriously impaired, because if you use any other, now if you give it, why I was doing it, because I was doing it on behalf of an electric power company to show them that is how given the last 7 days load, they can estimate next day's load, because they need to know when to send a boiler for maintenance. So what is going to be the load? So they need to anticipate it given the weather conditions, vagera vagera. Okay. So because my net learned this behavior, every time during that part of the year, even if you take another year, if you give another load, on that day it will give this kink, because it has learned to give that kink. So it is very accurate on the set of data on which it was designed, but it is too much accurate and it has lost its generalization capability. So if you compute on another set of data, you will actually get too much error on these points. So actually during neural net training, you should prevent the neural net from learning those features of the data which are not generalized. You should actually prevent the net there, should not train there. Okay, so that is very important. So when we are considering lower order estimators. So we are interested to know that if we have the MMSE, which is supposed to be grand because it is designed based on, it is supposed to be optimal over the whole stochastic process realizations, all possible realizations in an average sense. So now what we are saying, no, sorry, this is not what I am saying. What I am saying is that if you want to know the statistical properties, one obvious way of looking at it is that if y is actually here, this is not y hat, this is y, that is the data which you want to match using your estimate. Suppose y is actually generated with the same model that we are trying to assume, but only thing is that there are some additional terms. It is like as if the data y and x are actually generated using an FIR filter. Some x which you are measuring and some unknown FIR filter has generated y, the observation. We are just assuming. And then while sensing y, you have got some noise. Every sensor will give you noise. So here I have a noisy measurement of y and I have this x. This is a very common practical situation. For example, if you are having a control system, then why you will not consider x to be noisy? Because of the fact that x is, this is just I am giving an example, that suppose you are having a computer control system, so x is coming from your computer itself. So therefore you already have x, so there is no question of measurement. While y you are measuring through sensors, so therefore there may be measurement. This is just one situation. Okay. So we are assuming that the data has been generated actually using an FIR filter which is unknown. Now the point is that if I use the same FIR filter structure and then solve an LSE problem, will I get back these parameters which were used here? They are the so-called true parameters which were used to generate the data. If I use an least square estimate, will I get back those parameters? This is obviously if I get back, it is good. So we are saying that let y generate the data exactly in the same manner. That is, we are assuming that the data generation mechanism is the same as the estimator structure, only with an additive noise. It may or may not be same. In general, it is not same. You can data may be generated, let us say, by a 10th order filter, and you can still, it is still valid to try to estimate a second order filter. Nothing wrong in that. But in this case, we are just synthetically assuming that if a 10th order filter has been used to generate data, and if we are estimating a 10th order filter, then can I get back those parameters which were actually used in generating y? So after all, what is my C0? C0 is my LSE that is generated from y using that equation x transpose x inverse x transpose y. So now if you put y is equal to this, then you will find that the equation comes to this. X transpose x inverse x transpose. Now I will put this equation in terms of y. So x C0 star plus E. So this x transpose x. So this and this will get cancelled. You will get C0 star here. And then this multiplied by this. So you get this equation. So now you see that now we ask this question, that what is expectation of C0 star? That is, now this expectation is over what? Expectation is always over a random process. Which is the random process here? I have not said that x is a random process. X can be a very deterministic process. You can send a square wave to a system and see its response, triangular wave, whatever. So it's not necessary. So for x may or may not be random. We are assuming that this E is random because it's noise. Okay. So we are now taking the expectation. Whenever you take expectation, you have to know over what. So we are taking this expectation over all possible E's. Okay. So again, if we assume that now when do we say that obviously expectation of C0 is equal to expectation of C0 star. Now expectation of C0 star is C0 star, because we have used some values of coefficients to generate the data. It may be unknown, but it is constant, it is not varying. So therefore this is like C0 star, and ideally speaking you should put the expectation here outside, expectation of the whole quantity. Now when can you write expectation of the whole quantity is equal to this into expectation of this? That is, I am now taking the expectation inside only on this. This I am cutting out. When is it possible? If it is a deterministic sequence, it is possible. Otherwise also, if this random process and this random process are independent, then it is possible. But if they are not independent, that is, for example, if X itself contains E, then it is not possible. You have to remember this. So if, I mean, a very simple result is that if it is deterministic, or if you can take the expectation, then you can take, so you suppose if it is deterministic, then this is there is no expectation, it will come out, and you take this, and then if you have this as 0, then you get C0 star. So remember that the LSE will give you back the true parameters only under certain conditions. It will not give you the true parameters otherwise. In general, it is biased in the sense that if you compute, if data was generated in this fashion, and if you compute an LSE, and even if you take expectation, it may not come back to this. That depends on what is X and what is E and what are their mutual properties. Especially what will happen is that when we are using this kind of a model, sometimes we use an autoregressive model. That is, X contains past samples of Y. Now Y contains E. Y contains E. So the past samples of Y also contains the past samples of E. Now if the past samples of E and this sample of E are correlated, that is, they are not white, then this thing will not, you cannot write. So this situation, as we'll see in when we'll study identification, we'll see that various kinds of model structure. That's why the model structure is very important. What model structure we choose. Based on that, we may get a biased estimate. We may get an unbiased estimate. Some of you who are doing process monitoring and fault detection might have come across this. Okay. So we have no time to discuss the second point today, that is MMSE optimal IIR filters. But let me just start the discussion. We are going to repeat this. That is, so far we are always talking of FIR filters. That is, I am taking a finite number of sums. But I can take an IIR filter. I can take an infinite number of sums. So how do we calculate that? How do you calculate such a filter when there are infinite number of terms? So basically the thing is that finite or infinite, you always get the so-called normal equations or Wiener-Hoff equations. If they are infinite, you get the Wiener-Hoff equation, minus infinity plus infinity. That is, you first define this filtering problem, k equal to minus infinity to plus infinity. We are not assuming whether this filter is causal or non-causal. We are first defining a general problem, and we want to what is our objective? Our objective is to solve for these. These are the impulse response coefficients of the filter, causal or non-causal. We want to find out these such that the expectation of E square n is minimized. This is the problem. So it was given by the Wiener-Hoff equation that if you define that problem, then you can get these coefficients by solving these equations. Now the main problem is that you have an infinite number of equations and you have an infinite number of unknowns. So you can't even write them to solve it. So then how do you solve it? You can always define a problem nicely, but practically speaking, how do you solve it? So, so some people said that, okay, can I even solve it, I mean, sort of, non-parametrically, that is, can I get some closed form solution in terms of something? Here I am not getting any solution. I only say that if you want to get this, you have to solve these equations. Other than that, I cannot write the solution. So first thing is that people said that, okay, it's simple. I mean, at least you use Z transforms. So if you use Z transforms, then this is nothing but a convolution equation. So you write this as a product, H N C Z, NC for non-causal, because this goes from minus infinity to plus infinity. So you can easily define a Z transform and then use the Z transform properties. This will be Rxxz, this will be Ryxz. We know that the convolution in that time domain becomes multiplication in the frequency domain. So in the Z transform, if you take the Z transform of this and the Z transform of this, then this will be related like this. Then you simply define that H and C Z is this by this. So what does it give you? It gives you some H and C Z. It's some plot. You just compute this Ryxz as some plot, and you get, I mean, if you just happen to define this and this you can actually compute based on data. Then if you divide it, you will get this. At least you got some solution. You don't know how to do this so far, but if you could write the solution, then people say that, okay, this is fine. I mean, at least you can do it analytically, symbolically, but this is for non-causal. Now, in some application domains, non-causal filters are useful. They can be physically computed, like in image processing. But there are some domains where they are not useful because they cannot be computed. So there are some application domains where we have to restrict ourselves if we want to do anything practical, we have to restrict ourselves to causal filters. We cannot use non-causal filters. So what about that solution? What about the causal solution? So then people said that, okay, so now the causal solution, I mean the main problem of we will discuss this in more detail in a later class. Today we don't have time to go through it. But the main problem is that you cannot define, you see, this sum now is from 0 to infinity. It's not from minus infinity to plus infinity, because you are looking for a causal filter. You are trying to solve for a filter. So that filter must satisfy this equation, and this equation is defined, that is your filter, it will be a causal filter. So these are going to be 0 for k less than 0, right? So which means that now obviously if you have this equation, you cannot write a Z transform equation for k is equal to minus infinity to plus infinity. You cannot take, because you don't have values. Okay, you cannot define autocorrelation functions. Okay, so therefore people are saying that, well, so we'll see in a later class that people will take a slightly roundabout way to compute the solution. I mean, not through a direct Z transform technique, because a direct two-sided Z transform cannot be taken. So what people will nicely do is that they will use the innovation process. That is, they will first from X they will generate a white process using slightly different filter. I mean, using a filter which is causal. See, we are always looking for a causal filter. So whatever we generate, we must use causal filters. So first of all, what we will do is that we will see that how from X I can generate a white sequence using a causal filter. As we have seen that given random vectors, they can be made into uncorrelated random vectors, which are called innovations. And we have, so given a random sequence X, we can construct a corresponding random sequence W, which is white. That's called the innovation sequence for X using linear filters. So since I mean the argument goes like this, that since you have generated W from X using a linear filter, therefore W is equivalent to X. So the problem of estimating Y from X is the same as the problem of estimating Y from W, because you can generate W from X. So now you do it in two steps. First, from X you generate a white W, and from that white W you generate Y. So that's called a whitening process, and that actually clarifies the maths. So we'll do that in the next class. Today we don't have time, and okay. So the